TypeScript is the one tool as a web developer that has had the greatest impact on my coding, and that's quite a statement considering a few years back I had no interest in learning it. I only got into it because the company I was working for decided to use Flow, another static type checker with similar concepts for a project. In this video, I'm going to give you an introduction to TypeScript with the basic concepts, and I'll add in a few useful tips and tricks. Initially, I was reluctant to learn TypeScript because I started off learning JavaScript, so I wasn't comfortable with strongly typed languages. And I just found strongly typed languages unnecessarily verbose and clunky, having to be compiled to run rather than just interpreted at runtime like JavaScript. Since then I've backtracked, and I've found that the tooling associated with TypeScript, which you get in the IDEs such as VS Code or WebStorm, means more bugs are caught by the compiler, so you can refactor quickly and early. The compiler will catch errors before it fails at runtime, so you can find issues without having to watch your code blow up in the browser. Type annotations means your code is documented in the IDE itself, so you don't have to refer to online documentation for library and packages you use. When you write types, you're also providing a layer of documentation to your code base. This is a little bit of compassion for the next developer who has to look at your code, which may happen to be yourself. TypeScript being a superset of JavaScript also means it is pretty easy to pick up for JavaScript developers. Vanilla JavaScript code is also valid TypeScript, so you can learn as you code, rather than having to learn something completely foreign. Type checking is also optional, lowering the learning curve even more. JavaScript has gone through many iterations, and the problem we have is always, can we use this feature or that feature in the environment where we run our code? Using TypeScript means we don't have to worry about this, as we can use the latest features of JavaScript and then compile a code to whatever version of JavaScript we want. As TypeScript compiles into JavaScript, to get started you will need a TypeScript compiler and a TypeScript editor. I'll be using WebStorm as the editor. Any text editor can theoretically work, yes, even Notepad, but I will recommend an IDE which gives you access to TypeScript's documentation as you code. For the TypeScript compiler, we can install that by running npm install -g TypeScript. Once installed, this will give you access to the command tsc, which runs the TypeScript compiler. For this video, I'm running TypeScript version 5.3.3. Now we have a compiler, let's create our first TypeScript file. To do this, we just type touch index.ts. Now that we have our file, let's log out a hello world. We cannot run a TS file in the browser, so let's compile our TS file down to JavaScript. We do this by running tsc index.ts. This creates an index.js file with our console log. This is the file we will run in our browser or other runtime environment, such as Node.js. Without configuration, our compiler, version 5.5.3, compiles our code down to ES5, which was released in 2009. We're going to just add some code which is within the ES5 specification to see what happens. Here's a variable called isArray, where we are calling the array.isArray function, and a variable called str calling the string.trim function. As you can expect, when compiled, the file still remains identical. Now let's add some code from the later ES6 specifications. Const and let were part of the initial ES6 specification released in 2015, and async functions were added in the later ES6 2017 revision. For const and let, the compiler has just converted them to vars, and for the async function, you can see it has added all this crazy code just to get it to work with an ES5 compatible environment. The compiler can be tweaked by passing in some command line options. However, for most TypeScript projects, you would create a tsconfig.json file in the root directory of your project to define the options. This file will automatically get loaded when you run the command tsc. To create a tsconfig.json file, the easiest way is to run tsc --init. This will create the file with some pre-configured options, as well as add a list of other options commented out. There are so many options which you can configure based on the project you are running and what runtime environment you are targeting. The target property in compiler options is where we set the runtime JavaScript version. By default, it is set to ES 2016. If we set this to ES 2017, you can see now all that code for our async function is no longer being added. To compile down to the latest version of JavaScript, we set the target to ES next. As you work on different projects involving TypeScript, you may come across the following common config options. We'll go through them here, but won't set them for our own project. Out_dir. Currently, we have compiled JavaScript file in the same directory as our TypeScript file. In actual projects, you will generally want to put all the compiled files in one directory, such as a build or output directory, so that the files can be easily deployed. Allow.js and check.js. Allow.js means JavaScript files will be compiled as well, whereas check.js will allow you to start checking for errors and reporting on existing JavaScript files. The two properties are useful if you are starting out and want to incrementally add TypeScript to an existing JavaScript project. Source map. Source maps are a useful tool for debugging and fixing minified JavaScript code without the hassle of determining where in the original code an error occurred. They provide a way to translate between minified code designed to decrease web page load times to the source code the developer writes. Remove comments. Remove comments strips out the comments from our compiled files. This is an essential part of minification. Include specifies an array of file names or patterns to include in the program. These file names are resolved relative to the directory contained in the tsconfig.json file. In our example, we have added the src and test directories and using a glob wildcard pattern to include all the descendant files. So far we've been calling tsc index.ts every time we make a file change and want to compile our ts file. If we have multiple ts files, we would just call tsc and the compiler would find all the ts files in our project folder. If we want the compiler to watch for changes and automatically recompile when changes are made, we can run the command tsc-w. There are two ways you can strong type your code: implicitly or explicitly. Imagine we have a variable which is declared and assigned a string. Its type will be automatically inferred as a primitive string. This is implicit typing. As a side note, let's delve a little into primitive types in JavaScript. A primitive value in JavaScript is data that is not an object. It doesn't have properties or methods. In JavaScript there are 7 primitive data types. These are string, number, big int, boolean, undefined, symbol, and null. Primitive values are immutable, that is, they cannot be changed. You can change the assignment of a variable, such as var or let, to another value, but that means the assignment has changed to another value, not the value itself. A simple way to demonstrate this is to try to mutate the string. Let's create a variable and assign it a value of Paul. If we call to lowercase on name and log out the variable, the value is still Paul with a capital P. If we call to lowercase on name and assign it to name variable, then the name variable changes to lowercase. However, in this situation we have created a new value and assigned it to the variable name rather than actually mutated the original value. This is different from an object or array, which are known as non-primitive or reference data types. In this case we have an object person with a property, name, assigned a value of Paul. Now if we reassign the value of name to be donkey and log out the object, you can see that the object has changed. In this case we have mutated the person object by assigning a new value to the name property. Now back to TypeScript. We can explicitly set a type to our declaration by adding a type annotation or type signature straight after declaration. For variables which have an assignment straight after declaration, it's not necessary to explicitly state a type, as it is already implicitly inferred by the assignment. It is only useful if we are assigning the value at some later stage. Whether implicitly or explicitly typed, if we attempt to assign a variable to an incorrect value type, we will get an error from the compiler. These errors can cause havoc in a normal JavaScript application. However, with TypeScript, you can catch them early on. You can opt out of the type checking by explicitly using the type any. This is a last resort if you really do not know how to fix a type error. However, it is frowned upon and developers who see you use this will probably eye roll. The reason for this is that if you opt out of the type system too much, you may as well just use JavaScript on its own. You can also create your own types. These can be primitive or reference data types. You need to give your type a name, which is conventionally in Pascal case, and assign a type definition. Here we are defining a shape for an object, contact details. You can see here we have added question marks to some of the properties, which means they can be undefined. Only the first name and the last name are mandatory. After that we can declare a variable that's annotated with our type. If we add a property that is not defined, you can see the compiler complains. Let's make our type more complex by consuming a type within a type. Union types. Here we have another type called union. A union type describes a value that can be one of several types, with each type separated by a pipe symbol. For contact type, we only have different values of strings, whereas for age we have multiple primitive types. We create these types and use them in contact details type. You can also create an intersection to break up the types even further. Related to union types, an intersection type combines multiple types into one. This allows you to combine one or more types to get one type with all the features you need. Here we have separated the properties in contact details into two separate types, primary details and additional details. We then reference them in contact details and join them together using the AND symbol. Intersections are useful to describe when you are merging objects together. Here we have separate objects for primary details and additional details and merge them together to create the contact object. Now let's move on to arrays. You can annotate a variable as an array by adding a primitive type followed by two square brackets. Here we have a number of primitive type arrays, years with numbers, writers with strings, and options with booleans. If we try to push to the years array, you can see pushing the incorrect type will result in an error. Again, implicit typing works here as well. Since all our types are the same primitive, we can remove the explicit annotation and the compiler will infer a number array or string array or boolean array. So we can do away with the typings. You can also have an array of any data type, but in this case you may as well just go back to writing plain JavaScript. For objects we can use the object reference type to annotate an array. This is just as pointless as using any in the previous example, since an object without a defined shape could take on any shape. Let's make this more helpful by explicitly defining the properties for a book type, giving it a title and author. If you want to be pro, you can also mix in some union types. Here we have an array that can take string, number or boolean. If you created this in real life, I would question why, since anywhere you are using this array, such as using a map function, you will need to type check each item before using it. But this is just to show it is possible. If we feed the array some more values, as long as it is of the correct type, then the compiler won't complain. Let's get to some more complex union types. Here's a good time to introduce interfaces. Interfaces are another way to describe the shape of an object, similar but at the same time different types. You can probably write an encyclopedia about the two, but suffice it to say that types are preferred for primitive values, unions, intersections, tuples and functions, whereas interfaces are preferred for objects. Interfaces are said to offer better error messages and type checking performance. Let's use examples to demonstrate. Imagine we have a variable library, which is an array that can hold books and magazines. Libraries section off books by fiction versus non-fiction, so we need to take this into consideration when designing our interface. We also want to reuse our code from earlier, particularly our books and our book type. Firstly, we're going to define a book section union, which can only be fiction or non-fiction. Next, we will create a magazine interface to handle having an extra type of medium in the library. As you can see, the interface syntax is different from describing an object with a type. For comparison, this is how it would look as a type. We then want to make use of this union by creating a new interface called categorized book. But rather than redefining the same properties as our book type, we will use the extend feature of interfaces to inherit all the properties of the type book, and then just to add the additional book section property. This ability to extend off other types and interfaces is one of the most useful features of interfaces, and is something I use all the time in React TypeScript projects for sharing props between parents and child components. To finish off our library, we need to populate it with some magazines and books. We can just map over the books array from earlier and just add the additional type property to the new array, rather than rewriting the same array. Within the map function, you may notice the as keyword. This is known as a type assertion and is used to help the compiler by explicitly telling it what type we're expecting. In this case, the compiler is looking at the value fiction and inferring a string type. However, we are using it in the context of our book section union type. So in order to get the compiler to understand what we are trying to do, we do the type assertion to tell the compiler explicitly this is a type book section. To finish off our section on arrays, TypeScript allows for something found in other programming languages known as a tuple. In mathematics, a tuple is an ordered sequence of values. In TypeScript, it describes a typed array, meaning an array of predefined length where the type of each item in the array is defined. So here we're just defining our tuple type, my tuple, and it's made up of an array of a number first, then a boolean, and then a string. We're just going to create a variable in tuple we trust and annotate it with our tuple type, and then we're going to initialize it correctly. You can see the compiler doesn't complain, and then we initialize it incorrectly, and you can see the compiler notices that the type is in the wrong order. When we declare functions in TypeScript, we can define what types the function argument should be. as well as the return type of the function. Here we have a function getErrorMessage, which takes two arguments, error, which is a standard error type, and prefix, which is an optional string, and the function returns a string. We can also rewrite the function using an ES6 arrow function. Notice how in the arrow function the variable and the return type is inferred, so we do not need to explicitly annotate these types. Now, what if our function has no return type? Here we have a function logErrorMessage, which calls the getErrorMessage function and logs out the result. As there's no return value, we use the void keyword as a return type. If we want to describe our functions, such as in a type alias or an interface, we use function type expressions, which are syntactically similar to arrow functions, but replacing the function block with the return type. Classes have properties and methods, and so typing a class will just mean mixing what we've already seen with types, interfaces, arrays and functions. Here we have a class called Pokemon with 3 properties and 1 method. The main thing to point out is the typings for the class properties are written in the class block. Class methods can have return values implicitly inferred, just like standalone functions. We can also use the class as a type definition. In the myPokemon type, we are only allowing an array of Pokemon instances. Part of creating software is keeping your code dry, which means don't repeat yourself, as opposed to wet, write everything twice. Good software building means building reusable components, which makes your code base smaller and easier to maintain. Something that helps with this is generics, which is a component that can be used over a variety of data types, rather than a single one. Users of generics can consume the component but use their own types. To illustrate, let's create a function, addTimestamp, for adding timestamp properties to any API response object. As we want this method to be generic to work with any data returned in the API, we annotate the res argument of the function as object. We also annotate the response type as an object as well. When we call our function and then try and access the ID property, the compiler complains the property ID does not exist on the object. This is because we have not told the compiler what shape we have passed to the function argument res. This is where generics comes in. Let's write this function to be a generic so we can handle different API responses. Firstly, before we define the opening argument, we will add these angle brackets with a generic type t. This tells TypeScript we're working with a generic function. We then define the res argument as of type t, and annotate the return type as an intersection of type t with the additional timestamp property. You can see here that already the compiler has stopped erroring, even though we have not told it what shape our response is. The reason being, we have already told the compiler this is a generic, that the return type will contain the object passed as the res argument, so TypeScript is clever enough to implicitly infer that we have the ID property, as that was part of the original object passed in. We can also explicitly define the shape of the object passed in as the res argument, like so. Okay, everything looks good so far, but we have hit a problem. T could be anything, whereas we are only really looking for objects, specifically object literals. We could change this code by saying T extends from object, but then an array is also an object in JavaScript, so we still have a problem. Since we're working with API responses, chances are there's some form of unique identifier in the data. In our case, let's assume all API responses will have a number ID and extend T from an object literal that has this. Now you can see in the compiler that it no longer accepts an array as an argument. You can also use generics with interfaces and classes. Here's an interface called names, which allows the user to define what is the type for the ID property. And here we have a class restaurant, and we're allowing the user to define what the shape of the menu will be. We will finish this video by looking at enums. Enums are one of the few features of TypeScript, along with generics, which is not a type level extension of JavaScript. However, they both appear natively in other languages. Enums are useful to define a set of named constants, which makes it easier to create a set of cases. TypeScript provides both numeric and string-based enums, but by default enums are number-based. To declare an enum, we use the enum keyword, followed by a name for the enum, usually in Pascal case. Here we have an enum keycode. It is a numeric enum with space initialized with 32. If we did not initialize the rest of the enum values, then TypeScript will auto-increment the values from 32 onwards. So enter would have a value of 33, caps lock 34, etc. By default, if we had no values initialized, TypeScript will initialize based off a 0-based index. So space would be 0, enter 1, and so on. Enums can also be initialized to string values. Here we have a compass in the enum. Enums are useful when you want to group a number of related constants. It can also make coding easier, especially if you want to access a member of an enum. You don't need to remember all the enum members. You can just let the ID IntelliSense give you the options. You can also create an enum with a mix of strings and numbers. But again, just because you can doesn't mean you should. This has been an introduction to TypeScript. Please check out TypeScript React series if you're interested in learning more. If you have any suggestions for future videos, please comment below. Thanks for watching.